In this lecture video, we're going to introduce Chapter 19 on electrochemistry. Electrochemistry is a topic that is covered or introduced in Chem 60 and Chem 101. A couple things that we've learned in previous classes, let's review here. Electrochemistry, we want to think of redox reactions. In a redox reaction, electrons are transferred. And there's a few definitions we need to memorize. Oxidation, stands for losing electrons, and reduction is gaining electrons. A couple ways to remember this. Oil rig, oxidation is losing, reduction is gaining. Leo, the lion, goes grr. Losing electrons is oxidation, gaining electrons is reduction. If one element is losing electrons, another element is gaining. So you cannot have oxidation without reduction. They always both occur in a given redox reaction. Electrochemical reactions. In electrochemical reactions, electrons are transferred from one species to another. And the best way to figure out if a reaction is a redox reaction or not is to assign oxidation numbers to every single reactant and product element in the reaction. And you can see if the oxidation numbers change, the reaction is indeed redox. We're going to go over on the next slide how to assign oxidation numbers. This is a topic that is covered in Chem 60 and reviewed in Chem 101, so we will review it again before we move on with the chapter. As we can see here, solid zinc has an oxidation state of 0 because it has no charge. Zinc 2 plus has an oxidation state of +2 because its charge is 2 plus. So what's happened here, zinc went from a charge of 0 to +2, or oxidation state of 0 to +2, so it lost 2 electrons, so that's oxidation. Losing electrons is oxidation. I can see that hydrogen went from a charge of +1, or an oxidation state of +1 to 0. That means electrons come in as negative charges. So if we become less positive, that means it gained electrons. It was reduced, and each hydrogen atom gained 1 electron to form the neutral H2 molecule. In order to keep track of what loses electrons and what gains them, we assign oxidation numbers. In this image, this is a reaction we do in Chem 60 lab. You put solid zinc into a solution of hydrochloric acid, and zinc does indeed dissolve in the hydrochloric acid, so you form zinc 2 chloride and hydrogen gas. So the bubbles you see here are the formation of hydrogen gas. Okay, here are the rules for assigning oxidation states. They are included in your study guide, so you do not need to write them down again. What I'm going to do is read over these rules and write down some examples as we go. Number 1, free elements have an oxidation state of 0. So for example, sodium has an oxidation state of 0. Cl2, 0. In this reaction, sodium plus chloride. Other examples for rule 1. If I have iron solid, the oxidation state is 0. If I have phosphorus, which comes as a 8-member ring, the oxidation state is 0. This is our oxidation state. So any element by itself has an oxidation state of 0. Rule number 2, monatomic ions have an oxidation state equal to their charge. So in sodium chloride, I know that's a sodium cation, right? It's an ionic compound, and a chloride anion. When you're looking at an ionic compound, you always want to look at what ions are involved. So for example, if I have Fe3+, the oxidation state is +3. If I have S2-, the oxidation state of sulfur is -2. If I have MgBr2, Well, I know this is an ionic compound, right? A metal and a nonmetal. So magnesium is a 2 plus ion, which therefore has an oxidation state the same as its charge, which is +2. Bromide is a monatomic anion, oxidation state -1, same as its charge. Rule 3. The sum of the oxidation states of all of the atoms in a compound is 0. So in sodium chloride, we've got a +1 and a -1, and that adds to 0. And that's exactly why we form ionic compounds the way that we do. Remember in Chem 60 when we learn about this, we say, okay, sodium is a +1 ion, chloride is a -1, so we need to make an overall charge neutral compound, therefore we have a 1-to-1 ratio cation to anion. You can see here also magnesium bromide, +2 for magnesium. Each bromide is -1 charged with a -1 oxidation state. So when I add my oxidation states +2 and -2, that does indeed equal 0, which is the charge of that ionic compound. Rule 4a. Group 1 metals have oxidation states of +1 in their compounds. For example, sodium is +1 in sodium chloride. And group 1 metals, remember those are the alkali metals, the first row in the periodic table, or the first column, excuse me. And the reason that happens, remember they want to lose 1 electron to be like a noble gas. Well, in their compounds, they're going to have a +1 charge, which is the same as the oxidation state. Follows through the same way with group 2 metals, or the alkaline earth metals. They're always a +2 charge in compounds, and they always have an oxidation state of +2. Rule 5, in their compounds, nonmetals have oxidation states according to the table on the next slide. And nonmetals higher in the table take priority. So let's look at that. So for assigning oxidation states, we're always going to follow, for nonmetals, we're going to follow these rules. Fluoride, oxidation state of -1. Hydrogen +1, oxygen -2. Group 7a, -1. So fluorine has higher priority, the halogens below that -1. Group 6a, -2. Group 5a, -3. Let's look at some examples for how to use this chart. For example, I have H2O. That means I have hydrogen and oxygen. I see on the chart hydrogen is higher in priority than oxygen. I have 2 hydrogens, and I have an oxygen. And our oxidation state, we're going to list here. So I know hydrogen, based on these rules, each is +1. Oxygen, I can see, is then -2, and that matches. Adding together gives a charge of 0, which is what we expect for a neutral molecule. Let's look at another example, nitrogen dioxide. And I can see on the chart, looking at NO2, oxygen is higher than nitrogen on the periodic table, group 5a. That means we assign the oxidation state of oxygen first. I've got 2 oxygens and a nitrogen. Each oxygen has a -2 oxidation state, and that is the same as the charge it forms when it is in an ionic compound. NO2 is covalent. And we assign the elements first that are highest in priority, and then we use the rule that molecules with a charge of 0, remember all of the oxidation states must add to 0. So if these 2 oxygens add to -4, this nitrogen must be +4. Okay. Let's look at another example. Nitrate, NO3 minus. Again, oxygen is higher in priority. And in this case, we have 3 of them. And 1 nitrogen. I know that each oxygen is -2. I know that all of the oxidation states, I feel like I skipped this rule in the previous slide. Let's check. I think I did. So going over this, the sum of the oxidation states of all of the atoms in a polyatomic ion equals the charge of the ion. And this is what we're going to go over right now. I see that the charge of this ion is -1. So that means that all of these oxidation states must add to -1. You can see that all of my oxygens are -6 total. So nitrogen must be +5 because -6 and +5 must equal -1. Another example, in O2-, oxygen is higher in priority. They must all add up to -1. Each oxygen is -2. So overall, the oxygens combined is -4. -4 plus X equals -1. X must be +3. So there are a few examples of how you assign oxidation states for molecular compounds. I'll introduce practice exercise number 1. Identify the oxidizing agents and reducing agents in this following reaction. What you're going to do, you're going to assign an oxidation state to every single element in the reactants and the products, and you're going to then figure out if they've changed. I'm going to give you some new definitions here as well. Oxidizing agents and reducing agents. So an oxidizing agent contains the element that is reduced. Remember, gaining electrons is reduction. The reducing agent contains the element that is oxidized. Remember, losing electrons is oxidation. So if I myself am losing electrons, that means I'm giving them to the other reactant in the chemical reaction. Therefore, I'm reducing the other reactant. So go ahead, assign oxidation states to every single element in the reactants and products. We'll go over the answers in the next lecture video.